Okay, so in the last two classes, we discussed about the measurement techniques of low and medium range resistances. Now, I mean, in today's lecture, we'll conclude with the discussion of some methods to measure high resistances. So those are in the range of the value is greater than 0.1 mega ohms and above. Now, in today's class, I'm going to discuss three methods, which are the direct deflection method, mega ohm bridge method, and a device device called mega or mega ohm meter. So these three techniques I'll try to discuss today. And first of all, let us begin with direct deflection method. So insulation resistances are normally considered to be high resistances. So it could be cable insulation provided in a cable or between any electrical conductors. So for discussing the direct deflection method, let us consider the case of a coaxial cable. So you know the construction of a coaxial cable, that there are three layers. The inner layer is, you can refer it to be the inner conductor. Then in the middle layer you have the insulating material, and in the outer layer you have uh, the outer conductor. So the focus will be to determine the insulation which is provided by this insulating material by determining what resistance it is providing, because it is not nothing can be 100% perfect. So some leakage, some current will flow through the insulating material. So what would be the overall resistance provided by a particular insulating material, that is necessary to determine to design a particular cable. Now, for the direct deflection method, this method is quite straightforward, like measuring the supply voltage and the current flowing through the inner conductor to the outer conductor in order to determine the resistance. However, some factors have to be considered, because apart from the current flowing through the entire volume of the insulating material, some current flow through the surface of the insulating material as well. So to separate those two components of the current, that has to be considered while measuring the insulating resistance. So this direct deflection method, you can refer it to voltmeter ammeter method as well, because we are going to use a voltmeter in order to determine the voltage from the supply, and the ammeter to determine the current flowing through the inner conductor to the outer conductor. So this is the supply voltage, and an ammeter is connected to the inner conductor, and the circuit is completed by connecting the other terminal of the voltage source with the outer conductor. Now, in order to measure the supply voltage, the voltmeter should be connected here, not after the ammeter, because in this case, as the current is passing through an insulating material, it is going to face a huge amount of resistance. So very small amount of current will flow. So that is why the ammeter is denoted here in microampere range. And if the voltmeter is placed after the ammeter, then the current which will flow through the voltmeter, that will be more significant compared to the current flowing through the insulating material. So to avoid that aspect, in this case, the voltmeter should be connected directly across the source. However, for other cases, connecting it before or after the emitter doesn't have too much significant effect that it will have in this case. As the current is very low in magnitude, so very high voltage has to be supplied so that some amount of current can flow through the insulating material. So the voltage can range from 500 volts to 1000 volts to up to maybe 5000 volts even. So for measuring this high resistance, the operation has to be conducted at very high voltage as well. Now, like I was saying, there will be two components of the current which will flow through the inner conductor to the outer conductor. So if I draw the diagram of the cable, suppose from this side, if you watch from this side, or you can say the top view, so this is the inner conductor, this is the insulating material, and this is the outer conductor. So some current will flow through the entire volume of the insulating material towards the outer conductor. So that current is I mean, measuring that current is our concern over here. However, there will be some current which will leak through the surface of the insulating material. So we want to omit that portion, the leakage current. So the current which is flowing through the entire volume of the insulating material, the resistance that this current is experiencing, so we can refer it to be volume resistance. And the current which is flowing through the surface of the insulating material, the resistance that this current is experiencing, we can call it to be surface resistance. Now, for this configuration, the current that is flowing through this branch or through the emitter, in this case, it is I equals, suppose the current which is flowing through the entire volume, we can refer it to be IR. So current from inner to outer conductor. So the entire volume, and IL, we can call it the leakage current. Through the surface. So at this point, both the currents are flowing through the emitter. So the resistance that we can measure using the simple Ohm's law, that will actually have both the volume resistance and the surface resistance, or component of both of them. However, if we want to eliminate the effect of the leakage current, then we have to create a bypassing path so that the current IL doesn't pass through the emitter. It is bypassed before it is passing through the emitter. So for that reason, a wire can be used which will be connected with the surface of the insulating material. So this sort of connection using a wire is called guard wire. Now the current IL will now, as this is a short circuit path, it will bypass through this one, and the current IR, which will be flowing through inner conductor through the entire volume of the insulating material to the outer conductor, that will pass through the emitter. So in this way, the two currents can be separated, and now the volume resistance RV can be calculated as V divided by IR. And if you want to determine the surface resistance separately, then you can change the connection of the emitter from this point to here. So in that case, you will be measuring IL. So in that sense, you can measure the surface resistance as well. So in this way, you can separate the two resistive components provided by the current flow through the insulating material. Now, this was the case in case of coaxial cables. Now, if there is only an inner conductor and an outer insulating layer, then a slightly different approach has to be used so that the current passing from inner conductor through the outer conductor, sorry, there is no outer conductor, current which will be passing through the inner conductor and coming out of the insulating material, that can be collected somehow. So one of the approaches could be to use saline water, that is in a chamber. If saline water is taken, which can conduct electricity, then in that chamber, if the cable is placed, suppose this is the conductor portion and this is the insulating material, so then one terminal of the emitter can be connected with this inner conductor. Then we'll have our voltage source, and the circuit can be completed by placing a metallic contact in the water, so that the current which will be passing through the insulating material, that can be collected by the water, and a path can be established in order to make the current flow. So by doing so, the insulating resistance of this insulating material can be measured, and again, if the two current components are to be separated, then a guard wire can be connected with the surface of the insulating material. So this is the direct deflection method, or you can say the voltmeter emitter method, which is quite straightforward. Now,
Sir, will there be any problem if I place the voltmeter after emitter?
Yeah, there will be some problem, and that was I mentioned while discussing this circuit, because for this case, as the magnitude of the current is very low, so that will be a factor, because when you are going to connect the voltmeter over here, suppose if you place the voltmeter over here, the insulating material is providing you very high resistance. So the voltmeter will actually try to work as your load, and the most of the current which will be passed through the emitter will be the current which is flowing through the voltmeter. Okay, so not through the, it will not solely measure the current which is flowing through the insulating material, but it will measure the current as a summation of both of these currents. So if I refer it to be IV, then the current that the emitter is measuring is actually I equals I plus IL plus IR. So in that case, this current IV will be very much significant compared to these two currents, because they are in, suppose, microampere range. So that is why we cannot place the voltmeter after the emitter for this particular high resistance measurement. Even for lower medium range resistance measurement, this will be an issue, but in that case it will not have significant impact, but in this case it will have a significant impact. Is it okay?
Yes, sir.
Now, the previous slide, in order to separate the two currents, guard wire was used, where a wire was used to make a winding across the insulating material. So sometimes it might happen that we are not dealing with cables, but we are dealing with a sheet of insulating material, which would be in circular shape or rectangular shape or in any form of a shape. So in those cases, instead of guard wire, a terminal is attached with that particular insulating material, which is called guard ring. However, the purpose is the same, to eliminate the leakage current, or separate the leakage current, not eliminate. It will be there. So suppose this is a circular, so this is actually the cross-sectional view. Suppose we have a circular insulating material. So in order to measure the current which will be flowing through this insulating material, we need to place some probes or contacts so that we can collect the currents from both ends. So suppose this is the upper conductor, this is the lower conductor, and along with that, on the top of the surface, another contact will be placed, which can be referred to as the guard ring. So the purpose of the guard ring would be to bypass the leakage current which will be flowing through the surface. Now, if I draw it over here, so with the outer periphery of this circular insulating material, a ring will be placed, which we can call the guard ring, and it will serve to bypass the leakage current. And at the center, we will have the upper plate. So this is upper plate, we can define it as A. The lower plate, we can define it as B. And this is our same as our A, and this green one is the guard ring. So in order to
Sir, I did not understand the figure.
Okay, so let me repeat it. So suppose instead of a cable, now we have a insulating material available to us, only an insulating material, which is of circular shape. Okay, so this is suppose the top view of that particular insulating material, and this is the cross-sectional view. Suppose we have taken a cross section and we are viewing the material. So in order to connect the insulating material with the voltmeter or the voltage source, we need some connecting leads or connecting terminals. So suppose at the top of the insulating material, we have to connect some metallic contact so that we can connect this thing with our other circuit elements. So suppose in this figure, this is that top metallic contact, and in the cross-sectional view, that metallic contact is represented by this one. And similarly, on the bottom of this insulating material, there will be another metallic contact. So we can term that metallic contact to be the bottom plate, as indicated in this cross-sectional view, because from the top view I cannot actually show you. So in the cross-sectional view, you can consider this one to be the bottom plate, and surrounding this upper plate there would be another set of conducting material placed in a ring shape, which is shown by this green outer circle. And in the cross-sectional view, I can show it to be this, because there is a certain separation between the metallic contact and the guard ring. So in the cross-sectional view, I can show it like this. So the purpose of the guard ring would be to bypass the leakage current. So the current which will be suppose flowing through the surface of the insulating material, so that leakage current can be bypassed through the guard ring. Is the figure okay to you now?
Yes, sir.
Hello?
Yes, sir, it's okay.
Sir, it's okay, sir.
So later, if we connect it in the same way for the coaxial cable, like we did for the coaxial cable, so we can connect the supply voltage through an emitter with the upper plate, and the other terminal of the voltage can be connected with the lower plate of the structure. Now, if there is no connection in the guard ring, if there is no connection over here, then it will be same as both the currents I equals IL plus IR will be flowing through the insulating material. Now, if we similarly, like we did for the coaxial cable, if we put a wire and connect it with the guard ring, then the leakage current IL will be actually bypassed through the guard ring towards the lower plate, and the other current IR, which is flowing through the entire volume of the insulating material, then that can be passed through the upper conductor through the insulating material to the lower conductor. Now, in this case, as we are using circular shape, we can try to represent the volume resistance and surface resistance in terms of their volume resistivity and surface resistivity. And as we can calculate the resistance using the reading that we'll get from the voltmeter and ammeter, the resistance value will be known, then the volume resistivity and the surface resistivity of this material can be calculated. Now, before that, just let us define some dimensions for this structure. So suppose the diameter of the lower plate is D2. So that will be same as the diameter of the insulating material, because they are having the same area. Now, the diameter of the upper plate can be considered to be D1, and let us consider that the relation between D1 and D2 is like this. So D2 is twice of D1. So in that sense, you can say that D1 will be equal to the radius of the insulator. And the thickness of the insulating material, we can consider the thickness to be T. Now, for the volume resistance, we can define it to be RV equals rho V, the volume resistivity, multiplied by rho L by A. So L in this case, the length of the material through which the current will flow, that would be nothing but the thickness of the material. So we can write it to be T, and the cross-sectional area of this particular structure, as we are considering circular structure, that can be referred to as pi d1 square, as d1, the diameter of the upper plate, is equal to the radius of the insulating material. Now, this RV, this can be easily calculated from the voltmeter ammeter reading. So it could be V divided by IR. So once RV is known, then the volume resistivity can be calculated as from this expression. Now, if we consider surface resistance, then it can be defined in terms of the surface resistivity, then length of the current flow, length of the material through which the current will flow, and for surface resistance, it will be defined in terms of the perimeter, or in this case, you can say for circular object, we can consider the circumference. So we can define it as rho into T divided by pi d2 in this case, which actually represents the circumference of this particular structure. So similarly, yes.
Why are we taking the perimeter?
Because the leakage current is flowing only through the surface. So we are taking the entire length of the surface. Okay. Instead of taking the entire area, we are only considering the total length that is covered by the circular structure. So the total length, you can actually refer it to be equal to the circumference in case of a circular shape, and for rectangular shape or square shape, you can refer that to be equal to the perimeter. Is it okay?
Yes, sir.
So in order to determine the value of RS, you can disconnect the ammeter from here, connect the ammeter over here. So now in terms of V divided by IL, you can determine the surface resistance. And once you know the surface resistance, you can also calculate the surface resistivity to be equals to RS into pi d2 divided by d. Now, if this is the circular shape, the leakage current will only flow through the surface, not through the entire volume. So that's why only the length of the outer periphery is considered. So that is equal to the circumference of any circular shape. Now let us move on to the second method, that is the mega ohm bridge method. Now before moving to this part, let us refer to this structure again. Suppose this is the upper plate A, this is the lower plate B, and this is the guard ring, which can be referred to as terminal G. Now, in terms of the symbol of resistance, we can represent it as in the form of a delta connection, or as a three-terminal resistance. First of all, we can refer it to be like this. So there are two terminals A and terminal B, and there is an extra terminal G. So this resistive symbol will represent here the volume resistance of this particular material, and apart from that, there will be two additional resistances due to the surface leakage current. So one would be the, due to the leakage current flowing from terminal A to terminal G, or from the upper conductor to the guard ring, and another portion that is going to be flowing through terminal B to terminal G. So in that sense, if the resistance between these two terminals and these two terminals are considered, then a delta connected form can be considered. Here it would be terminal A, this would be terminal B, and this would be terminal G. So this is R, the volume resistance, same as before. Now the surface leakage resistance from terminal A to G would be, we can define it as RAG, and the resistance between B and G, we can refer it to be RBG. Now this is the equivalent circuit representation of this particular structure. Now let us consider the mega ohm bridge method. So in this method, the Wheatstone bridge circuit is used. Instead of the, in place of the unknown resistance R, so instead of the unknown resistance R, now we can consider the connection of this insulating material along with the corresponding connecting leads. So in terms of the circuit symbol, we have represented like this. So let us redraw this delta connected network over here. So this is A, B. So our goal would be to measure the volume resistance of between these two terminals, and using the guard ring, we would like to make the connection in such a way so that the effect of these two leakage resistances can be eliminated. So can you guys suggest that at which node should we connect this ground guard ring so that the effects of RBG and RAG can be eliminated or minimized? There are 4 nodes available here. So at which node should we connect the guard ring so that we can somehow minimize the effect of RAG and RBG, the leakage resistance?
The A node.
Here, are you referring to this node?
Yes, sir, maybe.
Yes, sir. He said A.
So can you suggest, why you are referring to this node, or how it may eliminate that effect?
By that way, the RAG resistance is being shorted. So no current will flow through that resistance.
Okay, but your RBG is still there, right?
Yes, sir.
So what will happen if we connect it here at this node? Well, that would be actually the case. It has to be connected here. But what would be the advantage of connecting it here? So while you obtain a balanced condition in a Wheatstone bridge, now what is the potential difference between the two nodes across the galvanometer?
0.
So if the potential difference between the two nodes across the galvanometer is 0, then as we are connecting RBG in parallel with the galvanometer, so the potential difference across RBG should also be 0. So no current is supposed to flow through this path. So effect of RBG can be eliminated in this way. On the other hand, your RAG is connected in parallel with P. Now, as we are dealing with insulation resistances, suppose the insulation resistance and associated leakage resistances, it will be in mega ohm range, suppose 100 mega ohms. And let us say that, okay, P is suppose 10 kilo ohms. Now, both of them are connected in parallel. So if they are connected in parallel, the equivalent resistance will be closer to which value? 100 mega ohms?
10 kilo ohms.
So it will be even lower than the 10 kilo ohms actually. So in that case, we are eliminating the effect of this high resistance. So if the guard ring is connected at this point, then through these two mechanisms, both the effect of RBG and RAG can be minimized, and the significant current which will flow, it will flow through the volume. And from the balance condition, then normally what the equation we normally use, the simple equation of Wheatstone-Risch that can be used to determine the unknown resistance or the volume resistance. Now, lastly, today, let me discuss something about the mega ohm meter, or which is also known as the Megger. So this meter is also used in order to measuring high resistance, or any form of resistance can be measured actually, but normally for I mean determining cable fault or measuring high resistance, this device is used. Now, the advantage of this device compared to the other methods is that it is calibrated in terms of resistance, so you don't have to use separate voltmeters or ammeters. Using this instrument, if you connect the resistance across the two terminals of this instrument, you can take the reading directly in ohms. So let us have some introduction on the components that are I mean available or that consist in this meter. So the basic mechanism for the movement of the pointer of this in this device is the PMMC mechanism, or the permanent magnet moving coil mechanism, because you can see there is a permanent magnet in this device, and in between the two poles, if this is the north pole and this is the south pole, in between the two poles there are two conductors, I mean winding of conductors. So one is this one, the shown by the white rectangle, and the other one is shown by the black rectangle over here. So and both of those windings are connected one way or another with the supply voltage. So some currents will flow through both the windings, and as the windings are placed in a magnetic field, so the current carrying conductors will experience some force, and that force will actually cause the pointer to move in a particular direction. Now we have two coils over here. So one is the control coil, as referred over here, control coil. Now the control coil, if you look at the connection of the control coil with respect to the supply voltage, so these are the two terminals of the windings. So this is a current limiting resistor, Now, if you don't consider the resistor for the time being, you can see that the two terminals are actually, in some sense, they are connected in parallel with the supply voltage. So for that reason, the control coil is often referred to as the potential coil as well. And the other coil, which is referred to here as the deflecting coil, is often referred as the current coil. Why it is referred as the current coil? Because the unknown resistance Rx that we want to measure, we are going to connect it in between these two terminals. Now the current which is flowing through this resistance will be the same as the current flowing through this deflecting coil. So from the supply voltage, the same current will flow through the deflecting coil through the unknown resistance, then towards the other terminal of the source. So it is carrying the current which is flowing through the load resistor, I can say. That's why it is the current coil. On the other hand, the potential coil, it is almost in parallel with the supply voltage and also in parallel with the load. In that sense, you can suggest it to be as the potential coil. Now the two current limiting resistors, that are these two are necessary in order to limit the flow amount of magnitude of current which is flowing through both the control coil and the deflecting coil, because for high resistance measurement, high voltage source is necessary. So if the current limiting resistors are not placed along with the windings will burn out. So for that reason, these two resistances has to be put over there, and in between the two windings, a magnetic material is placed, or magnetic core is placed, so that the magnetic permeability can be enhanced. Now, this is the in general the construction, and apart from the two terminals where you have to connect your unknown resistance, there is another terminal provided by the meter, that is the guard ring terminal. So the guard ring which is available with the insulating material, that guard ring has to be connected with this terminal of the meter. So suppose if I represent it in terms of the delta network that we saw a little bit earlier. So suppose this is terminal A, this is terminal B, and this is terminal G, or the guard ring. So the guard ring of that structure should be connected with this terminal. Now the operating principle. Okay, regarding the structure, is there any confusion to anyone?
No, sir.
Okay, so now to discuss the operating principle, the winding of the two coils, the control coil and the deflecting coil, will be done in opposite direction. So if the winding is done in opposite direction, they will induce opposing torques or experience opposing torques. So the winding in the control coil is done in such a way that in presence of the magnetic field, the control coil will produce a counterclockwise direction force, or it will experience a force in the counterclockwise direction, and the winding of the deflecting coil will be done in the opposite way. So the force that will be experienced by the deflecting coil will be in the clockwise direction. So with these movable coils, a pointer is attached. So the pointer will move depending upon how much resultant force these two coils are generating. So if the control coil is carrying more current than the deflecting coil, then the resulting deflection will be in the counterclockwise direction. And if the deflecting coil is carrying more current compared to the control coil, then the deflection will be, resultant deflection will be in clockwise direction. Now, if you look at this scale, the two extreme points are marked as 0 ohms and infinity. So the infinity is actually representing the open circuit case, and 0 ohms is representing the short circuit case. So we can consider these two cases separately. Now, when these two terminals are open, where we were supposed to connect any unknown resistance, we keep these two terminals open, then what will happen? That the path for current flow through the deflecting coil will not be completed because there is no resistance Rx now. So there will be no component in the resultant torque that is coming from the deflecting coil. All the deflection is resulting from the torque that is being experienced by the control coil, because all the current is now flowing through the control coil when these two terminals are open. So the pointer will now move in the counterclockwise direction, and it will be located at the extreme point in the counterclockwise direction, that is labeled as infinity to represent the open circuit. On the other hand, if we consider the short circuit case, for the short circuit, these two terminals will be shorted without putting any resistance. They will be directly shorted using some conductor. So if that is the case, then most of the current will actually flow through the deflecting coil as a result of the short circuit. And for this node, where there is two possible paths for current flow, obviously the path where there is a short circuit, that will be followed, and this path which is having a resistance, it will be ignored. And as a result, in this case, most of the current will be flowing through the deflecting coil, and as a result, the resultant movement of the pointer will be in clockwise direction in this case, and the pointer will now be located at the extreme point in the clockwise direction, which would be denoted as 0 ohms to represent the short circuit. And for any particular resistance which is connected in between these two terminals, there will be some current flowing through each of the coils, and depending on which coil is carrying the more current, the deflection of the pointer will be according to that resultant force. Now, apart from the 0 ohms and the infinity, the midpoint can also be defined in terms of R1 and R2, because at the midpoint, the two coils are going to be having same share of the current. The current will be equal through both the coils, so the resulting force will also be equal, and there would be an equilibrium state between the two coils. So at equilibrium, or at any point, the current which is flowing through the deflecting coil, we can refer it to be V divided by R1. Although there will be some resistance of the winding of the coil, but for the time being we can ignore it, because R1 would be more significant or higher compared to that resistance of the conductor. And similarly, for the deflecting coil, the current can be flowing through the deflecting coil can be referred to V divided by the summation of R2 and Rx. So at equilibrium, both of these currents should be equal, and from here you can easily say that for this case, your unknown resistance should be equal to R1 minus R2. So this middle point at the scale can be actually referred to as R1 minus R2, the difference between these two resistances. And similarly, the other points can be proportionally defined by testing with some known quantities of these known quantities of resistances connected between these two terminals. And once the scale is calibrated properly, then later on it can be used for unknown resistances as well. So this is the general working principle of this particular meter, which is explained in terms of this simplified circuit representation. Now, regarding today's lecture, if you have any question, you can ask. Otherwise, this concludes our discussion on measurement of different types of resistances.
No questions, sir.
Okay, so in your book, you will find another method, which is loss of charge method, which I am not covering here, but you can go through it on your own. It is dependent on charging and discharging of a capacitor, which would be connected in parallel with the resistance that you want to measure. So the charging and discharging of the capacitor would be dependent on the time constant of this unknown resistance and the capacitance, which is denoted by RC. So if the capacitance value is known and the charging and or discharging time can be determined, then in terms of the supply voltage and the voltage drop across this node up to which the capacitor is charged, depending on those values, the unknown resistance can be determined. So I'm not covering it here, so it will not be included in your syllabus, but you can go through it from the book. And I'll try to provide you the article numbers, like I said, within this weekend, so you can start taking preparation, because maybe at the end of this month we may have a quiz, so you can start taking preparation for that. And after 7 weeks we are supposed to have our midterm exam. So as far as I know, we were having a discussion in our last class regarding the exam. One of you asked. So as far as I know to now, that for midterm the exam will be a written exam, and for the semester final there would be a combination of written exam and a viva. So your midterm will be a written exam, so you can keep that in mind and take preparation accordingly. And the quizzes, I haven't decided yet, but for the quizzes maybe there would be a short question based exam, or maybe I might take online exam in Google Form or something like that. So for quizzes it could be like short question based exam, and for midterm, as it would be a written exam, the question patterns will be similar to what normally you get in your physical written exams. So
sir, what is the probable date of the first quiz?
the last week of this month, I would prefer that. If it was earlier, then it would be it would have been better, but for me the last week of this month would be better for the quiz.
Okay, sir.
By this time, for the other courses you can take the quizzes, as I am already declaring that I will take the quiz at end of this month. So by this time you can finish your quizzes of the other courses.
Yes, sir.
So I'm finishing